Thank you for the invitation, and thanks, Ron, for this kind introduction. So I will probably need to explain what geometric deep learning is. So I will start with an historical parenthesis, but maybe first of all, I need to mention that what I'm presenting today is based on a joint work, a book that we're writing now with Joan Bruna, Taco Cohen, and Petra Veličković. So you can find some more materials on this website. Self-explanatory geometricdeeplearning.com. So let me take you back in history for where geometry was born, right? So this is ancient Greece, and from Euclid's fundamental work, basically this is the only kind of geometry that we knew for more than 2,000 years, right? What we nowadays call Euclidean geometry. Nothing else existed, and in fact, one of the Euclidean postulates about parallel lines stubbornly defied any attempt to prove it. So it was a kind of, you could prove other things, but this one was special. And the dramatic event that happened, or it's actually not a single event, but multiple people were working at the same time, came to the realization that you cannot prove it, so it's independent. So you can construct other kinds of geometry where this postulate doesn't hold. And somehow projective geometry is not considered a non-Euclidean geometry, but it existed before. But probably the first construction of non-Euclidean geometry properly, the credit goes to Nikolai Lobachevsky in 1826. Then even Gauss himself amused himself with these ideas, never published. Janos Bolyai, and then Riemann, Gauss's own PhD student. Basically, the bottom line is that there emerged an entire zoo of different geometries towards the end of the century, and it was not even clear how they are related and which geometry is the true one, how to define a new geometry. And this created a little bit of unhealthy situation, the way out of which was shown by Felix Klein. So he was only 23 years old when he was appointed as full professor at the University of Erlangen in Germany. And as the tradition went, and I think it still goes in Germany, he was asked to deliver an inaugural program about his research at Erlangen. And this entered the history of mathematics as the Erlangen program, where he proposed approaching geometry as the study of invariants or symmetries. So these are properties that would remain unchanged under some class of transformations. And this immediately brought clarity, showing how different geometries could be defined if you appropriately choose these symmetry transformations. And he also used the shiny new tool of group theory that he also, well, you can say, co-invented together with Sophos Lee and maybe previously Galois to describe these transformations. And for example, the classical Euclidean geometry could be derived from the assumption of rigid motions, Euclidean transformations that preserve angles, areas, parallel lines, and so on and so forth. And this was very powerful and very perspective-changing idea, and it had a big impact on mathematics. So all modern geometry, you can say that Cartan continued these ideas, right? And category theory, actually, its creators stated themselves that this is an evolution of the ideas of Erlangen program, but it also entered into the field of physics. And Amy Neuters, actually, I should say that also another historical factoid that Klein spent only 3 years at Erlangen, and he moved around a little bit, eventually settling at Göttingen. And Amy Noether was then a young mathematician that happened, unfortunately, to be still in the period where women were not allowed to teach and hold faculty positions, but nevertheless, she was absolutely remarkable. And she proved a fundamental result in physics, showing that you can derive conservation laws from first principles of symmetry. So this is what is known as Noether's theorem. So you can apply it to variational formulations of physical problems. And this is really remarkable because before that, conservation laws were completely empirical. So you would derive them from experiments. And here you can, for example, derive conservation of energy from the principle of symmetry of time. And this became a very prominent topic in physics. And Hermann Weyl proposed the idea of gauge invariance, that it evolved a little bit. I think his first result was incorrect. Then in 1954, Young and Mills used this idea to show the unification of forces. And basically, this is what from the 70s is called the standard model. It describes all the physics we currently know. Well, maybe with the exception of gravity, so you can derive all physics from these considerations. And I can quote here Philip Anderson, who was a Nobel-winning physicist, that it's only slightly overstating the case to say that physics is the study of symmetry. So it's really very fundamental. Now, of course, we are talking about deep learning here, so you may wonder what at all does it have to do with deep learning. And I think in some sense, the situation in this deep learning is reminiscent of the situation in geometry in the 19th century. So on the one hand, of course, deep learning has really created a revolution in data science, especially in some fields such as computer vision, natural language processing, speech recognition, and well, playing intelligent games such as Go, or maybe recently protein folding. On the other hand, we have again this unhealthy situation. We have a zoo of different architectures of different types of neural networks that are designed for different kinds of data, but very few unifying principles. And as a consequence, it is very hard to understand relations between different models, when certain models work and when they don't. And inevitably, there is also a kind of trend of reinvention and rebranding of the same concepts. And well, again, unhealthy situations, so sometimes people fight over priority. So what geometric deep learning attempts to do is some form of geometric unification in the spirit of the Erlangen program. And it serves, first of all, the purpose of providing a common mathematical framework where we can describe, analyze, and derive from first principles some of the most popular and successful neural network architectures. And second, it is also a kind of constructive procedure that would allow, hopefully, to build future architectures in a principled way. So it's a principle that probably will go beyond the particular implementation. For example, backpropagation-based learning that is now popular. So the term itself, I can take the credit for inventing it. So I made it up for my ERC grant in 2015, and it became popular after a paper that we wrote in the IEEE Signal Processing magazine. And nowadays you can find it used almost synonymously with graph neural networks, but I hope to show you a way broader picture. So let's maybe look at machine learning in the simplest setting, right? So this is the typical example that you're given supervised learning, which is essentially a function estimation problem. So we're given the outputs of some unknown function that is visualized here by this black box that takes inputs, so let's say images of cats and dogs, and these images are labeled, right? So our function produces binary output, whether it's a cat or a dog. And what we try to do in supervised learning is we try to find a function from some hypothesis class that fits well the training data. And we hope that it would allow us to predict the outputs on the test set, on previously unseen inputs. And what happened in the past decade, and what made actually deep learning successful, is that two trends coincided. So first of all, it's the availability of large and high quality data sets, such as ImageNet, which contains millions of hand-labeled images. And second, the computational power, in particular using graphics hardware, GPUs, that allow to design rich function classes that have, at least in principle, the capacity to interpolate such large data sets. And neural networks actually appear to be a suitable choice, even though they're not new at all, right? So perceptrons, for example, what I show here, date back to the 50s. We know that if we combine it, just two layers of perceptron, we can produce a dense class of functions. So we can approximate any continuous function to any desired accuracy. So this is a property that is called universal approximation. But the problem is that, of course, the setting of this problem in low dimensions has been studied very extensively in approximation theory, and we have a lot of results on the error bounds, right? We can say how exactly we need to sample our input in order to have an error smaller than certain number. Unfortunately, these bounds do not work in high dimensions. And you can easily see that if we take even very nice, very regular function class like Lipschitz continuous functions. So the example here, I take Gaussian blobs and put them in the quadrants of the unit hypercube. So we see that when we grow the dimension of this space, then the number of samples that we need to take in order to guarantee certain error will increase exponentially. So this is one of the manifestations of a broader phenomenon that is called the curse of dimensionality. And unfortunately, in most, I would say 99.9% of machine learning problems, we need to operate with data that has not 10 dimensions and not 100 dimensions, but how about thousands or millions of dimensions? So the curse of dimensionality is a built-in problem, if you want, in machine learning, and it's always there, and that's why these naive approaches to learning are intractable. And this is probably best seen in computer vision problems like image classification. Even very small images tend to be very high dimension, right? So if you take the MNIST digits, these are 32 by 32 pixel images, so it's almost 1,000 dimensions. And the way that you would naively approach this problem, you would just parse the image into a vector and pass it into the perceptron neural network. But of course, intuitively, you see that you have this two-dimensional geometric structure that is broken and thrown away. And if, for example, I just shift the image by 1 pixel, I will get a very different vector. So the vectorized input will not survive this transformation. And what we need to do is we need to augment the data. So we'll need to present the neural network with a lot of examples of shifted digits to make it come to the conclusion that these are all the different instances of the same class, right, of the same digit. And the remedy for this problem in computer vision came actually from works in neuroscience, or at least the inspiration for it, that show that the connectivity of brain neurons is organized into what is called local receptive fields. And a new class of architectures using shared local weights, first the neocognitron by Fukushima, and then the classical CNNs, the seminal work of Jan LeCun. Basically, they allowed to effectively solve the curse of dimensionality by sharing the weights across the image. So this is the situation that where you can share weights when you have an underlying grid. But here is another example. So this is a molecular graph that is commonly used in chemistry to represent molecules. So the nodes represent atoms and edges represent chemical bonds. And here again, so if you're wondering, actually, this is a molecule of caffeine. So I guess we all like it. Me in first place. And if you were to apply a neural network to this input, for example, to predict, I don't know, some chemical properties such as atomization energy of this molecule, which is a very common task in, for example, drug design and drug screening. So again, we can take the node features, pass them to a neural network. But the problem is that we don't have any canonical arrangement of the nodes, like we had an image where, for example, we can column stack our pixels. Here, any permutation of the nodes will do. So we already see that we have to deal with completely different structure. And there are many prominent examples where this kind of non-Euclidean irregular data is important to deal with, such as social networks, right, like Twitter, the follow graph or other graphs that Twitter has, or interactomes or interaction networks in biological sciences, meshes in computer graphics, right? So these are graphs on steroids, these are simplicial complexes, and so on and so forth. So what I will try to convince you is that if not all hope is lost, so if we look at this problem where we suffered from the curse of dimensionality, we actually can use the structure that often underlies our data, and we can exploit this structure as some form of geometric prior that will allow us to break the curse of dimensionality. And this will turn a general, very powerful principle that can be applied to a lot of different problems and structures. And in our example, specifically of image classification, it is not correct to treat the image as a d-dimensional vector. So you lose a lot of information. You need to consider it as a signal that is defined on some domain, which in this case happens to be a two-dimensional grid. And we can describe the structure of the domain by a symmetry group. So let's say the group of 2D translations, which acts on points on the domain. And in the space of signals, the group actions are manifested through what is called the group representation. So just to make things concrete, in our case, it will simply be the shift operator. So it will be a D by D matrix that acts on a D-dimensional vector. So I should say that here there is a subtle point that the domain which you assume, you typically get, you can infer it from the data, right? So if you have an image, then of course the underlying domain is a grid. What kind of symmetry structure depends very much on your application, and it's more nuanced. So we typically assume the translation group, but imagine a situation where you have, for example, let's say that the problem you want to address is traffic sign recognition, right? So when you have a self-driving car. So typically signs, they don't come in a lot of orientations. So translation will probably capture the kind of variability you have in your data. But if you have, for example, a plane that flies over the road and needs to recognize traffic signs, then you also have rotations, right? Still, you don't have reflections because this is not physical. But if I look at a different problem, like analysis of histopathological samples, where I have a slice of a tissue that I put under the microscope, then I can put it in any possible way, right? I can translate it, I can rotate it, I can also reflect it, right? So the kind of symmetry group that you need to assume in your problem depends a lot on what you're trying to achieve, okay? But the bottom line, the structure of this group imposes certain structure on the functions that take as inputs to these images or general signals on the domain. And we can have functions that are unaffected by the action of the group, what we call invariant functions. And a good example is image recognition. So here we say that I don't care where the cat is located in the image. I want to say that this is a cat, right? So this is an example of shift invariants. We might have different kind of problems where the input and the output space is the same, right? So if I want to label every pixel in the image to segment it, and in this case, I can talk about group equivariance. So the output is transformed in the same way as the input. And actually, the output doesn't need to have the same structure. So for example, my feature maps can be higher dimensional than the input. So that's why, in general, this representation in the output might be different from the input one. So another important principle is the principle of scale separation. And maybe it is less prominent in physics as symmetry, but still it's a very important principle. And actually, this is what allows us to abstract physics and write it as a set of equations, right? So maybe a good example, I sit now in the room and I have quadrillions of gas molecules that are flying around, colliding, right, with each other. So if I were to describe this system on a molecular level, of course, it will be intractable. It will have a zillion of degrees of freedom. But fortunately, if I zoom out and I look at it at macroscopic scale, then there might be just a few degrees of freedom, such as temperature, that very faithfully describe this system of interactions. And if I zoom out even further, if I look at the Earth from the planetary standpoint, right, at planetary scale, I don't care about all these intricate compositions and non-homogeneity, right, and the kind of winds that flow in the atmosphere. It moves like a material point when it orbits around the sun, right? So I can abstract it out. So that's exactly the idea of scale separation. And in machine learning, we can, in some cases, construct a hierarchy of domains and define a space of signals that are related by a coarse graining operator and apply our function at these different scales. And a nice kind of functions, what we call locally stable functions, are such functions that can be approximated as a composition of this coarse graining operator and the coarse scale function that I denote here by f prime. So it's not a derivative, it's a function that is computed at the coarse scale. And what happened is that while the original function might depend on long-range interactions on the domain, in these nice locally stable functions, it is possible to separate these interactions across scales. And this is exactly what convolutional neural networks do. So if you combine these two principles of symmetry and scale separation, you have a very general blueprint that we call geometric deep learning. And you can really find its instances in the majority of popular deep neural network architectures. We typically apply a sequence of equivariant layers like convolutional layers and CNNs. Then in some situations, maybe some global invariant pooling layer that aggregates everything into a single output, like in the image classification problem. And we can also create this hierarchy of domains by some coursing procedure that typically corresponds to some form of local pooling, right? Like max pooling in convolutional networks. And these ideas can be applied to very different structures, such as grids, more general homogeneous spaces where we have global symmetry, right, where the groups act transitively, graphs and manifolds, where we have different kinds of global and local invariants. And we can actually show that the implementation of these principles can be, basically, we can derive some of the popular deep learning architectures, such as CNNs, graph neural networks, deep set transformers, different versions of mesh intrinsic CNNs from the same blueprint by just choosing the domain, the group structure, and the resulting invariance and equivariance. And I hope to show you today as well that these methods are also very practical, and they allow to address a broad variety of problems from understanding how proteins fold and interact that can lead to the design of new drugs to detecting fake news in social media. So let me start with graphs. I think graphs are a very popular abstraction for different systems of relations and interactions. And in particular, to have this mental picture of a graph, think of a social network where you have users that are modeled as nodes of the graph, right? And their friendship or social relations as edges. And let's say that we also attach some d-dimensional vectors to each node that model some properties of these users, some demographics, for example, right? So this will be our simple model of the graph. We can, of course, make it more complex. We can attach also features to the edges of the graph, but let's consider a signal that lives on the node set of the graph. So one thing that you need to understand when talking about the graph is that it's a purely topological structure, right? So it doesn't really have a canonical ordering of the nodes. So when I take my feature vectors and arrange them into an n by d matrix, right? N here is the number of nodes and d is the dimension of the features, I already prescribed some arbitrary ordering. So why still it's convenient? Because again, I can represent features as matrices and I can represent the structure of the graph in the form of its adjacency matrix, where I have a 1 in the place at position ij, where there is an edge between nodes I and j, and 0 otherwise, right? Of course, you need to understand that if I provide a different ordering, I will have different structure of this matrix. So I will need to permute my matrices by a matrix that I denote here by P. And this is exactly the representation of the permutation group. And we can actually see that, again, this is maybe slightly subtle technical detail, it acts differently on different structures. So on vectors, it acts by leftwise multiplication. On matrices, you need to permute both rows and columns. So we need to multiply from the left and from the right. Okay, but bottom line, if we want to implement our geometric deep learning blueprint, we might have two kinds of functions on graphs. So if I have a function that provides a single output for the entire graph, right? Remember this problem where we try to predict some properties of a molecule. I want to be invariant to the permutation of the nodes. So no matter how I order them, I want to produce the same, let's say, energy, right? So this function will be permutation invariant. We can also have either as intermediate layers of our graph neural networks, or as maybe solving some node-wise tasks, such as detecting, for example, badly behaving users on a social graph. We might have functions that change in the same way, the output changes in the same way as the input. So these are permutation equivariant functions. And we cannot have really the most general class of such functions because they will not be computationally tractable. This permutation group is too large. But a way that is, as I will show, is sufficiently generic is to look at the local neighborhood of a node. And we look at the nodes that are attached by an edge to a node I, aggregate their features. And together with the feature vector of the node itself, we can create, we can apply some function that will create a new set of features of the graph. We apply that at every node of the graph, right? So there are two important things here. So first of all, the neighbor node features form a multiset. We might have the same feature that appears more than once, right? So a multiset is a set where the same element appears more than once. Another important thing is that we don't really have a canonical order of the neighbors. So this local function that I denote by phi must be permutation invariant. And if we apply it at every node of the graph and arrange the output into a matrix, it is easy to show that the output, this function f, is permutation equivariant. So if I apply this permutation invariant local function phi at every node, the result will be permutation equivariant function. And it appears that the choice of this function phi is very important on the expressive power of the resulting graph neural network. And if this phi is chosen to be injective, we can show that the neural network designed in this way is equivalent to what is called the Weisferler-Lehmann graph isomorphism test. So it's a classical algorithm in graph theory that tries to determine if two graphs are isomorphic, or in other words, if there is an edge-preserving bijection between the two graphs, right? Or whether I can permute one adjacency matrix into another by means of permutation P. And the way that the Weisferler-Lehmann algorithm works, it starts with a graph that has all the nodes labeled in the same color, right? And color in this case is a discrete label. And what it looks is, it looks at the neighborhood structure. So in this initial graph, we have two types of neighborhoods, right? So I have a blue node with two blue neighbors, and I have a blue node with three blue neighbors. Because phi is injective, it will be assigned to different new labels, right? So the first one will become green and the second one will become yellow. So it's a kind of color refinement procedure. I can apply this procedure once again, and now we have three kinds of neighborhoods, right? So I have green node with two yellow neighbors. I have a yellow node with a yellow neighbor and two green neighbors. And I have a green neighbor with a yellow and a green neighbor, right? And these will become violet, red, and gray. But if I apply this procedure once again, then the colors will not change. So at this point, I can output their distribution, and this will be a kind of descriptor of the graph. And the Weisferler-Lehmann algorithm guarantees you that if I give you another graph and the resulting color distribution will be different, I can for sure say that these graphs are not isomorphic. But if the distributions are the same, then actually I don't know. So in other words, it's a necessary but insufficient condition. And in fact, we can find examples of graphs that will be considered equivalent by the Weisferler-Lehmann test, but they are not isomorphic. Like an example here, you can see that the graph on the right has triangles, the graph on the right has rectangles, and you can show that the Weisferler-Lehmann test cannot count triangles. So you can easily see it because basically it considers rooted trees at the node, and in these graphs, they will look exactly the same. So there are more powerful algorithms there. So there is an entire hierarchy of what is called KWL tests that consider higher order structures in graphs that are strictly more powerful than these tests, and there are equivalent graph neural networks. So what was shown recently, or actually not that recently, that a graph neural network of certain type that I will show now is equivalent to this graph isomorphism test. So let me say a few words about how a typical graph neural network will look like. So we have, first of all, some permutation invariant aggregation operator. Typically, it's a sum or a maximum. So it's actually important how it looks like. It should be an injective function to make this, architecture most expressive. We have a learnable function psi that transforms the neighbor features, and another function phi that updates the features of node I using the aggregated features of the neighbors. And fortunately, most of the architectures fall into one of the following three flavors. So the first flavor is convolutional graph neural networks. In this setting, we aggregate the neighbor features using some weights that depend only on the structure of the graph. You can think of them as a kind of importance of one node to the representation of another. And as I will show you on grids, this will boil down to classical convolution. Slightly more advanced architecture, this is what is called attentional flavor. So in this case, the coefficients depend not only on the structure of the graph, but also on the features themselves. So GATT, graph attention networks, is the most prominent representative of this flavor. And finally, the most general architecture, we have a generic nonlinear function that depends on both features of node I and j. And the output of this function can be regarded as a message that is sent to update the features of node I from node j. So these are message passing graph neural networks. And by the appropriate choice of these components, you can make it as expressive as the Weisferler-Lehmann test. Now, I hope you can see that this is just an instance of our general geometric deep learning blueprint, where we have the permutation group as our geometric prior, the graph as our domain, And typically we have a sequence of permutation equivariant layers, right? So this is what what is called typically propagation or diffusion layers in this literature. An optional global pooling layer, right? If you want a single readout, like in molecular property prediction. And we can also do some graph coarsening, so we can have some local pooling layers that can also be made learnable. So we can learn based on the downstream task how to coarsen the graph. That doesn't have immediate analogy, let's say in CNNs, because the domain is fixed. Here, the domain, the graph itself is part of the data, part of the input. Now, it is interesting to look at some corner cases, so that we can also see as special cases of graph neural networks. And the first one is to look at sets. So in case of sets, this is just a graph with empty edges, right? And it shares the characteristic of graph that sets are unordered. So we don't have a canonical order of elements in a set. And in this case, we can do two things. So we can either treat each node independently, right? So we can apply some shared function phi to the feature vectors associated with each element of the set. And this translates into a permutation equivariant function over the set. So again, this is a special setting of a GNN. So this architecture is known as deep sets in machine learning, or point net in computer graphics. It was applied to, for example, the analysis of three-dimensional point clouds. Now, another alternative would be to say that instead of saying that every element in the set acts on its own, we can assume that any two elements can interact. And in this case, we are talking about a complete, fully connected graph, right? And in this case, actually, if you try to apply the convolutional flavor of the graph neural network, you will see that it's superfluous, because the second argument of this function will be exactly the same. We're aggregating over all the set of nodes. So we need to use at least the attentional flavor. And I hope that you can recognize the popular transformer architecture, where you can interpret the attention as a kind of learnable soft adjacency matrix. So this is now the bread and butter of natural language processing applications. And you can see that transformers are also a particular case of GNNs. Of course, there is a little bit of cheating here, because transformers are typically applied to situations where you have sequential data, like words in a sentence. So in this case, the order of nodes is given, and this node information is typically provided in the form of positional encoding. So these are additional features, typically sines or cosines, that uniquely identify the node and allow you to tell where you are actually in your sequence, right, in your set. And these ideas can also be applied to graphs. So you can also do positional encoding in a graph to specialize the message passing function so it is aware of where it is in the graph. And there are multiple ways to do it. So what we did with my students is using structural encoding, counting some small graph substructures such as triangles and cliques, and provide it as a structural encoding to the standard message passing graph neural network. And we can show that with appropriate choice of these substructures that can also, in follow-up work, we show that they can be learned from the data. We can be strictly more powerful than the Weiss-Farrell-Lehmann test. And we can also interpret this kind of structural encoding as a problem-specific inductive bias, because we know that in certain data sets, certain structures are prominent, important, and even interpretable. So in social networks, for example, cliques tend to be such structures. In chemistry, these structures are cycles. So if you look at organic molecules, you will see that there are multiple cycles, like aromatic rings, or if you look at the my favorite molecule of caffeine, you have a 6 cycle and a 5 cycle, right? And if we count these cycles and we do some chemical prediction tasks, such as the solubility of the molecule, we see that this structure where graph neural network performs significantly better, right? And again, not surprising, because these structures are important in these applications. So basically, this is to say that even when we don't have the input graph neural networks still work. And there is a trend in the graph learning community to try to separate the input graph from the computational graph that is used to do message passing, because the traditional approach is you're given a graph, you're given the features on them, so use the same graph to propagate information. And this was put into question in recent works in different forms. For example, one of the standard things that you can do is to sample the graph, right? So the first motivation comes actually from scalability issues when you deal with gigantic graphs, such as the work on Graph Sage by Will Hamilton. You can also try to rewire the graph. So say that I can find a graph that is somehow similar to the original one, but is maybe more favorable. Maybe some form of denoising of the graph. Or you can look at multi-hop filters, where I aggregate not only from my immediate neighbors, but also maybe from the neighbors of the neighbors. So we did this kind of work at Twitter, where that we call sign or scalable inception-like graph neural networks. So bottom line, you don't need to stick to exactly the same graph. You can actually learn the graph on which you can apply the graph neural network, making it optimal for the downstream task. So this is a setting that is often called latent graph learning. And you can also change the graph throughout your graph neural network. So the first layer and the second layer do not necessarily need to use exactly the same graph. So the first architecture of this kind, we call it dynamic graph CNN. And we used follow-up work, this kind of architecture with collaborators from Munich to do classification of some neurological diseases of the brain. Now, maybe in a slightly broader and maybe more philosophical perspective, this kind of latent graph learning, you can relate it to nonlinear dimensionality reduction and manifold learning, where the premise is that even though your data is high dimensional, somehow the intrinsic dimensionality of the data is low, and a metaphor for it is to say that your data is sampled from some low dimensional manifold. So the typical example that is shown is this Swiss roll surface that is two-dimensional, but it is embedded in 3 or higher dimensional Euclidean space. And the typical way that manifold learning techniques work, they capture the structure of this manifold by constructing k nearest neighbor graph. So you have some local proximity, right, that is captured by the adjacency structure of the graph. And then you try to embed it into some low dimensional space where it will be more tractable to do some machine learning applications such as clustering. So if you think of methods like TSNE that are popular for data visualization, this is a form of nonlinear dimensionality reduction or manifold learning. The problem why it has never really worked beyond data visualization is that all these steps are completely separate, right? So you will first maybe even find some space where you represent this manifold, right? Then you will construct this nearest neighbor graph in some way. Then you embed it into some space, and then you do your machine learning. And of course, the way that you construct the graph hugely affects the way that the results of this clustering, for example, will look like. And nowadays, with deep learning architectures, we can put everything into a single end-to-end differentiable pipeline where we can build the graph and the filters that act on this graph, basically the machine learning algorithm, in the same package, right, as a GNN with a latent graph structure. And I mentioned the work that we did with colleagues from TUM. So we had a version of this latent graph learning architecture that we call DGM, or differentiable graph module, that we applied for automated diagnosis applications. And we show that it consistently outperforms GNNs with handcrafted graphs, because there are many situations in these healthcare applications where you don't know actually how your graph looks like. So you want to learn it based on the task that you are trying to do. Now I see that I'm a little bit short on time, so let me talk about grids, which obviously are a particular setting of graphs, right? So if you look at a one-dimensional grid with periodic boundary conditions, this is what is called the ring graph. And what you notice, first of all, that every node has exactly the same neighborhood structure, right? So every node has exactly 2 neighbors in this one-dimensional grid. And not only that, the order of the neighbors is fixed. And I remind you that in general graphs, we didn't have any canonical ordering of the neighbors, so we had to aggregate features from this multi-set of neighbors by a permutation invariant function phi. Now on a grid, I can order in a canonical way my features, and therefore this function phi is more specific. And in particular, if I make it linear, I get the classical convolution, which I can write in the form of a circular matrix that acts on the feature vectors. And you can see that the circular matrix essentially is constructed by cyclic shifts of a single vector of parameters that are denoted by theta. So that's exactly these shared weights that I mentioned at the beginning in convolutional networks. Now, the characteristic property of circulant matrices is their commutativity with respect to multiplication. And in particular, we can say that we can pick up one of the circulant matrices that cyclically shifts the element of a vector by one position. So that famous shift operator that I mentioned in the beginning, right, when we talked about the example of image classification. So that's exactly how it looks like. So circulant matrices commute, they commute with shift in particular. And this is just another way of saying that convolution is shift equivariant, right? I can first apply shift and then convolution, or vice versa, the result will be the same. Now, it is also easy to show that this statement works in the other direction. Not only every circulant matrix commutes with shift, but also every matrix that commutes with shift is circulant. And what we get in this way is that convolution is the only linear operation that is shift equivariant. And you see that actually it emerges from the assumption of translational symmetry. So again, this is a manifestation of our geometric blueprint. And I think also from pedagogical perspective, this is the right way of explaining what convolution is, because I think some signal processing preferences seen in defining convolution more or less out of the blue. So they give it as a formula, and this is what you do, right? So this is also how many references on deep learning explain what convolution is, right? A bit of hand waving and motivation from maybe receptive fields in neuroscience. And you can actually see, if you're familiar with representation theory, that this is part of a broader picture of irreducible representations, and you can actually derive the Fourier transform. Here in particular, you can say that circulant matrices are jointly diagonalizable, right? And their joint eigenvectors happen to be the Fourier transform. You can actually derive it analytically. You can look at the eigenvectors of the shift matrix, and you'll get the famous complex exponentials that form the classical Fourier basis. And this idea can be generalized to graphs. You can take either the adjacency matrix that serves as a shift on grids, or the Laplacian operator. In the Euclidean case, they're exactly the same. They have the same basis, the Fourier transform. In case of graphs, they're slightly different, but the ideas are exactly the same. Now, let me move a little bit to a more general case where our group formalism will be more prominent. And again, we can think of convolution as a kind of this shared weight operation, right? So in an image, I can implement it as a sliding window. So I apply my weights on a page of pixels at different positions in the image. So I can formalize it in the following way, right? So we can write convolution by having a shift operator that I denote by t, applied to the filter that I denote by psi, and for every shift, I match this filter to the image x, right? And to do the matching, I need to define an inner product. Okay, so if I do it for every shift, I get the convolution. So the convolution is computed for every position of the filter. Now, there is a little bit of cheating here, because actually I conflated here the domain and the group, right? And this is a special case because I can identify the elements of the translation group with points on the domain, on my in my plane or in my grid. Basically, the point to which I shift can be used as a representation of the shift. This is not the general case. This is a very special case. And in general, we have the filter transformed by the representation of the group that I denoted by rho. So we can actually show easily that this group convolution is group equivariant. So we can exchange it. We can exchange the position of this rho. But what you get here is that the output is defined for every group element. And the group structure might be different from the structure of the domain itself, right? So here's an example. Let's say that I want to do convolution on the sphere. So the sphere is, in this case, is S2. I can represent elements on this domain as unit three-dimensional vectors. And the group that we assume here is SO3, the special orthogonal group, right? So you can already anticipate that the sphere is a two-dimensional manifold, and SO3 is a Lie group, it's a three-dimensional manifold. So the elements of this group can be described as matrices that are denoted by R that are orthogonal that have determinant equal to 1, right? Determinant 1 means that they preserve orientation. So the convolution here, I define it as an integral on the sphere, but actually it takes elements for every element of SO3. So the output is in SO3 and not in S2. So if I now want to apply another layer of convolution, like I would typically do in a deep neural network architecture, I now need to do convolution on SO3, right? So this is how it will look like. So here the integral is over matrices that are points on this group, right, on this manifold. And in a sense, in CNNs, we are lucky that the input and the output space has the same structure. Here, it doesn't. And yet, if we look at the sphere, it is a non-Euclidean domain, right? It's a manifold, but it's still quite special in the sense that every point on the sphere can be transformed into another point by an element of the symmetry group of rotations, right? So there is, in a sense, complete democracy among the points, and we call such spaces homogeneous. And well, we can also say that the group acts transitively. So the key characteristic is this global symmetry structure. And of course, this is not a valid assumption for general manifolds. And for general manifolds, we don't have this immediate way of taking a filter and shifting it around or moving it around the domain by applying an element of the group, right? So I remind you that in case of images, I could take my filter, right, some local structure and move it by an element of the group to a different position. So the result would actually not depend on how I move it. On the manifold, of course, the situation is dramatically different. And if I take my local filter and move it along, let's say, this green path and along the blue path, I will get very different results, right? So this is what is called parallel transport. And basically it says because of the curvature of the space, the result of moving a vector on the manifold is path dependent. So one key characteristic of manifolds is that they're unlike the spaces that we've seen before, they are only locally Euclidean, right? So we can, in general, these are topological spaces, right, where we don't have a notion of distance, we have a notion of a neighborhood. And if we can map a small neighborhood on the domain around the point to a Euclidean space of certain dimension that we call the tangent space, so this we call this structure a manifold. And we can equip further the tangent space with additional structure in the form of an inner product that is called the Riemannian metric, and it allows us to measure locally distances and angles. And if we can deform the manifold without affecting the metric, we say that it's an isometry, which actually also forms a group. So we want, for example, in some applications in graphics to be invariant to isometric deformations. So this is a slightly subtle concept that I didn't have time to talk about. We talked about deformation of the signals. Here we're talking about deformation of the domain. And actually, well, Ron is very familiar with these concepts because he did some of the first works about the stability of graph neural networks. So what happens when I change the underlying graph, right, the underlying domain? Or if I have a signal that is drawn on some surface and I start stretching or bending this surface, what happens? What happens as a result, right? So if I tell you that if my function is intrinsic, right, if I can express it in terms of the Riemannian metric, then any isometry of the domain will not change it, right? So here I have guaranteed invariance. And this is a way of defining convolutions on manifolds, right? We can write it as some kind of local filter that is applied in the tangent space. And again, if we do all the constructions here, like the exponential map, for example, it's intrinsic, right? We get a construction that is invariant to isometries of the domain itself. And actually the first work that I did with my students was what we call geodesic CNNs, was exactly this kind of construction. Now, one thing that again is a little bit of cheating is that we are forced to work on the manifold locally where we don't have really a global system of coordinates. So in order to describe these tangent vectors, I need to, when I want to represent them as numbers on the computer, I need to express them with respect to some local reference frame, right? So this is what physicists call a gauge, right? So this is just a fancy word for a collection, a smooth collection of such local references. And unfortunately, we don't have a unique way of defining this gauge. It can be transformed more or less arbitrarily. So it really depends on the kind of structure that you assume. So if you have just naked topological manifold, it can be any linear transformation, any invertible matrix. So what we call the general linear group. If we have some additional structures, we can restrict it further. And if you have Riemannian metric, we have orientation and we have volume, right? So we can restrict it to orthogonal special orthogonal group. So in case of two-dimensional surfaces, it will be SO2. So essentially, the local frame is defined up to rotation. Okay, and you can construct these filters in a way that if you transform the frame in a certain way, the filter will be transformed exactly in the same way. So the filter will be gauge equivariant. Now, why this is interesting and why this is important, you may argue that manifolds are some exotic objects that arise in differential geometry, but not that interesting in machine learning. One motivation comes from the domain of computer vision and graphics, where we use manifolds, right, or the discretization as meshes to describe three-dimensional objects. And you can see this example where I have a deformable object like this checkered surface. And if I can define a filter intrinsically on the surface, then it will be invariant to deformations. And one class of applications where it comes prominently is this kind of motion capture, where we have a computer vision and computer graphics system that tries to transfer the expression of the actor to this synthetic character. So actually, the video that I show is technology developed by a Swiss company called PhaseShift that was acquired by Apple a few years ago, and this now powers the Animoji feature on the iPhone. And actually, there are two problems here. So one is finding correspondence between the input noisy surface captured by the scanner and the canonical mesh of the face. And the second problem, the problem of synthesis, where we try to deform this canonical mesh into the desired expression. And indeed, we had to use maybe a few years ago 3D scanners to achieve this effect. And Ron mentioned RealSense. I was involved in a startup that was acquired by Intel, and this was the technology of these low-cost 3D sensors. Nowadays, of course, with geometric deep learning, you can do it actually with standard cameras. So here is an example of a hybrid architecture where the input is a two-dimensional image or video that is encoded by standard CNN, and then the decoder is a mesh geometric architecture. And this was the work of my PhD student, Dominique Coulon, in collaboration with a British startup, Ariel AI. And we showed a demo of detailed hands and human avatars in real time, actually running 10 times faster than real time on a legacy smartphone. And the company was acquired by Snap last year. Well, I cannot claim much credit besides being one of the early supporters of the company and one who convinced the founder to leave his highly paid job at Facebook and do this startup. So I think I'm almost out of time. So let me say a few words about applications, and in particular applications of graphs and graph neural networks. And it's not surprising why graphs have become so popular in machine learning, because they're very generic abstract models for systems of relations and interactions that you can apply to model phenomena at all scales, from molecules to social networks. And we have our take on social networks, trying to detect fake news. So that was a startup that I co-founded with my students called Fabula AI, where we looked at the way that stories spread on Twitter, trying to detect from these spreading patterns what is fake and what is not, and were acquired by Twitter. So that's where I spent most of my time now. So probably the most interesting problems of graph neural networks that potentially can revolutionize this field is drug design. And you probably know that drug design is a very expensive business that can take a decade and about $1 billion investment to develop a new drug. And this has to do with first of all, the complexity of the search, because the space of potential molecules is humongous. And then, of course, the different stages of rigorous testing before you can actually inject or give a pill to a patient, ensuring that there will be no side effects and it will be effective against the disease. So it is common in the pharma industry to do what is called virtual screening. So you out of all the humongous number of this combinatorial search space of potentially synthesizable molecules, you want really to narrow it down to a few compounds that you can test in the lab. And graph neural networks actually were designed for this kind of applications. So message passing graph neural networks were come from motivation in quantum chemistry. And actually, there is a parallel universe in computational chemistry of works that invented graph neural networks before they became popular in machine learning for problems of predicting properties of molecules. Actually, the Weisfeld-Lehmann algorithm, its work from 1968, was inspired by the work in computational chemistry by George Badutz, who worked in the Soviet Union. He was probably the first one to model molecules as graphs. In the West, I think this credit is given to Morgan. It was published in 1965. So Badutz published in 1963. And he came to Weisfeld-Lehmann with the problem: how can we design a graph algorithm that allows to distinguish between different compounds? So, long story short, nowadays graph neural networks are actually used in pharma pipelines. So one of the big success stories last year was the work from MIT, where they used graph neural networks to predict antibiotic activity of different molecules and discovered a new potent antibiotic drug called halicin. And with my collaborators in Lausanne, we used geometric deep learning architectures trying to design new biological drugs that are based on proteins. So we can create de novo proteins completely from scratch that will bind to certain protein targets. And one of the applications is, for example, in cancer immunotherapy, of very flat interfaces that are typically undruggable by small molecules. And finally, probably the most exotic project that I'm involved is looking at problems of drug repositioning. So where you take molecules that are known to be safe, right? And you try to find different targets for them and use them against different diseases. And in particular, we're looking for food-based molecules. So take this idea of drug repositioning to the domain of nutrition. And you may know that foods that come from the plant kingdom are rich in compounds that come, for example, from the same chemical class as anti-cancer drugs, right? So this is not surprising. Actually, we see it in the names of many drugs. Even take such a trivial thing as aspirin. So the chemical name is acetyl salicylic acid. Salicyl comes from the Latin name of the willow tree, Salicia. And it was known from ancient time, if you take the bark and extract some liquid from it, so that would be, it has analgesic properties. So in the cancer therapy domain, the synthetic analogs of camptothecin, which is a compound found in the bark of a tree that grows in China called Camptothecum, is used against as a chemotherapeutic agent against cancer. So food is full of these kind of molecules. And most of them are still unknown. They are not tracked by regulators, so you will not find in the list of your proteins, carbohydrates, vitamins, and minerals on the food packaging. So this is truly the dark matter of nutrition. And the way that we approach this problem, we look at how molecules interact with proteins. And we describe proteins in the form of what is called PPI graph, protein-to-protein interaction graph. And we can use a graph neural network to train a classifier on, let's say, a data set of known anti-cancer compounds. And then we can apply this classifier to predict whether a molecule that comes from a food ingredient will have potential anti-cancer properties. And we use this approach to construct what we call a food map of about 250 different food ingredients and see whether there are interesting foods that have many such molecules. So this is what we call hyperfoods. And examples are tea, citruses, cabbage, and so on. So all the boring stuff that is actually quite healthy, apparently, and can, at least in principle, help you prevent cancer. So we are now trying to do some in vitro and in vivo experiments to see whether it actually holds water. But probably the nicest part of it, and I will stop here, is that we collaborate with famous chefs. And here you can see the Italian chef Bruno Barbieri, who directs the MasterChef Italy TV show. So he used our ingredients that we identified computationally to prepare recipes for Christmas last year. And if you wonder why he's in bed, this was a collaboration with Vodafone, a citizen science campaign called DreamLab, where we used the idle power of smartphones of Vodafone clients at night to make these computations, kind of distributed computing.